Alright, we finished part 5 by talking about the extra missing mass within galaxies. And we have 2 lines of evidence for this. We have the rotation curves of individual spiral galaxies, which rise from the center where all the matter seems to be because of all the light, and then instead of declining like we'd expect, it levels out. What that means is that there must be an extended dark halo of matter out here that we can't detect, or at least we can't see with any sort of radiation that it gives off. Okay. Another line of evidence of this is that the galaxies within clusters are moving around too fast for the clusters to hold together, and yet they do hold together. So that means there is also 10 times more mass in a cluster of galaxies than the stuff that we see, than the starlight and light from H2 regions and dust and everything like that that we can detect. Okay. Now, one way we can detect indirectly this missing matter is by something called gravitational lensing. We see examples of this with galaxies that are in the foreground of more distant galaxies. For example, this one right here is many, many millions of light years in the foreground, and this distorted blue galaxy back here is in the background. This isn't the actual shape of that blue galaxy, it's just that the light from that galaxy is being distorted as it goes around the intervening galaxy. Okay, so these are called Einstein rings, actually, gravitational lenses. And we can actually see this from in distant galaxy clusters. This is a tremendously interesting photograph. All the yellowish galaxies you see are in the foreground. All the ones that are stretched into arcs are many millions of light years in the background. And it's the gravity of this cluster, which is filled with galaxies and dark matter of the galaxies, that is bending the light from these distant galaxies into these long tendrils. Okay. Now, when if we sort of work backwards and see how much missing matter, how much dark matter do we need to make this kind of distortion happen, we can actually map out the dark matter. This is an image where the yellowish dots represent the position of galaxies in a foreground cluster, and that is gravitationally lensing galaxies in the background cluster. Those are not mapped out on this image. But the blue haze here is the distribution of dark matter. Okay, so the dark matter can actually be mapped out, even though it can't be seen or detected from radiation. It can be detected gravitationally, and we can work backwards using a supercomputer and the equations of general relativity to figure out that it's there and where it is. So, what is the dark matter? Well, there are several candidate explanations. The mundane ones, the ones that aren't as exotic, are dim low-mass stars. Okay, we know that there are a lot more low-mass stars than there are high-mass stars, and so if you add them all up, they add up to a significant amount of mass. We don't think there's enough of them, though. They're hard to find, but in our solar neighborhood anyway, we don't see enough of them to come anywhere near close enough to the amount we need. Same thing with brown dwarfs. Although more brown dwarfs have been found in the last few years, we still don't think there's nearly enough brown dwarfs. Brown dwarfs are sort of failed stars. They're somewhere in mass between the lowest low-mass star you can get and, say, Jupiter. In fact, Jupiter can almost be considered a brown dwarf. But in fact, we call it a gas giant planet. At any rate, all these things could contribute more mass than the mass that we see, but they just don't add up to anywhere near enough that we need to make dark matter. Exotic? Well, maybe there are millions and millions and millions of black holes that we can't see. Actually, that explanation has been fairly well eliminated. Black holes, if they were that plentiful, in our galaxy, for example, would cause something called microlensing, where if they pass in front of a distant star in for example, like the Large Magellanic Cloud, it would make it brighten. And so we now have robotic telescopes scanning those areas of the sky, and we don't see anywhere near enough microlensing events to account for that many black holes, at least not enough black holes that we would need to solve the dark matter problem. So it seems as though the only thing we have left are massive unknown elementary particles, some sort of different kind of matter that does not interact with radiation and does not interact at all with other forms of what we call baryonic matter. Baryonic matter is normal matter made out of protons and neutrons and electrons. So that seems to be the best guess so far. The problem is we haven't found any of those particles. And it's really hard to go through science with a hypothesis that has defied testing for so long. So the dark matter problem is still an unsolved problem. Okay, finding the distance to galaxies. We're going to be talking about very, very distant regions of our universe in the next unit. And so we have to be able to find distances all the way out to really, really distant galaxies. And this is what I sometimes call a house of cards, because every distance measurement is based on the most basic ones. And if those basic ones are wrong, the house of cards basically falls down. We usually use the distance measurement megaparsecs to talk about distances to galaxies. A megaparsec is about 3.25 million light years. Now, all the methods we're going to talk about ultimately rely on geometric parallax of nearby stars. So this is sort of the base of the house of cards. If the geometric parallax measurements are wrong, all the other measurements are off by a greater degree than we even thought. However, we have very recently, within the last 20 years, really, really, really pinned down the geometric parallax of nearby stars and even much more distant stars, and we'll talk about that in a minute. Spectroscopic parallax has been used to calibrate Cepheid variable stars in clusters in our Milky Way. And what we have to do is assume a uniformity of nature. In other words, if we're going to use Cepheid variables within our galaxy, we also have to think that they're the same in other galaxies. We don't think, for example, that Cepheid variables in the Andromeda galaxy are different than Cepheid variables in the Milky Way. We really just have to do that. We have to kind of say, look, we're stuck with doing that, and we don't see any reason why they should be any different. So distance indicators to other galaxies, what we call standard candles. Cepheid variables are the most reliable distance indicators for other galaxies. They work out to about 30 megaparsecs. That's roughly 100 million light years. That's a long way, but we can see out way beyond that. 100 million light years is beyond the Virgo cluster. I don't think it's beyond the Hercules cluster, though. So we still need a better method beyond that. The Tully-Fisher relation is kind of interesting. Tully-Fisher relation says that basically what we do is we look at galaxies that are within the 30 megaparsec range of Cepheid variables, and we plot it on a graph of rotation or mass versus brightness. And we find that, not surprisingly, for spiral galaxies, their rotation rate and their mass are related to the brightness. Basically, the more mass of the galaxy, the brighter it is. So the absolute brightness of spiral galaxies are related to their mass. Brighter galaxies seem to be more massive, so they spin faster. And since spin is correlated with brightness, we can estimate how bright the galaxy is by measuring its spin. So we can easily measure its spin using the Doppler shift, and then we can use this method to judge distances out to about 150 megaparsecs. Okay, again, 150 megaparsecs is, roughly a half a billion light years away. 150, about half a billion light years away. So basically, we use the galaxies themselves to figure out the distance to the clusters in which they are embedded. Now, another method that has become tremendously important and reliable in the last 15 to 20 years, I would say about 20, 25 years actually, is the use of Type 1a supernovas. Now, you may remember from the chapter on the deaths of stars that Type 1a supernovas are basically not massive stars that blow up, but they are white dwarf stars that blow up after they accrete material onto their surface and then reach or exceed the Chandrasekhar limit, and then basically implode on themselves and explode. And when that happens, it causes a supernova that is tremendously uniform in brightness. So when we see these supernovas in other distant galaxies, we know roughly how bright they are. And then by judging against how bright they appear in our sky, we can get a very good estimate of the distance to these distant galaxies. This has only become possible in the last 20 to 25 years or so because of the advent of robotic telescopes. It's impossible to scan all these galaxies every night if you are a human being. However, we now have robot telescopes that can be programmed to look at thousands of galaxies per night, compare their images to one the night before or the night before that, and then if we see a spot that wasn't there before, it flags that one and tells the humans, take a look at this, guys. It might be a supernova. And supernova curves for 1A supernovas are very, very well known. They're very uniform. And so that helps us get the distances to really, really far away galaxies. And so this is what we call the cosmological distance ladder. First we have parallax. Like I said, this was sort of the base of the house of cards. And the Hipparchus satellite has made this a much more strong foundation. Spectroscopic parallax is quickly becoming obsolete. It was very, very necessary up until recently, and within the next few years, the Gaia mission, which is sort of the follow-up to Hipparchus, but is much more sensitive and much more accurate and can go much, much farther. It goes all the way to the galactic center. So basically, this line will disappear very soon, and parallax will go all the way out to the galactic center. That makes these things more accurate and makes these things more accurate. And so the accuracy of all these methods are dependent on the one before them. And because of that, we can now go all the way out to 1,000 megaparsecs or more. So parallax, variable stars, Tully-Fisher relationship, Type 1a supernova. There's one more thing called the Hubble law. This was found in the 1920s. It was found that the more distant galaxies all had redshifts. And it turned out that the farther a galaxy seemed to be, the bigger the redshift in its spectrum. Okay, remember redshift is where the spectral lines are shifted toward the red. And the more they are shifted toward the red, the faster the object is going away from us. So what Hubble discovered was that all galaxies are going away from us, but they're going away in a very linear fashion. In other words, a galaxy that is moving about twice as fast is about twice as far away. And a galaxy that's moving 3 times as fast is about 3 times as far away. Okay. So he found this linear relationship in 1929. It turns out to be extremely important for the history of our universe. But that isn't something we're going to talk about until a couple chapters down the road in the next unit. If you make a graph of the recessional velocity, basically what you get from the redshift, how fast it goes away from us, versus the distance, it follows a very nice trend line here. And what we find is there is a very easy equation. It says that the recessional velocity is equal to the Hubble constant times the distance. We now know that the Hubble constant is approximately 72 kilometers per second per megaparsec. In other words, for every megaparsec in distance that a galaxy is away, its speed away from us increases by approximately 72 kilometers per second. This is a number that has only been pinned down in the last few years, and it's amazing that it used to be uncertain by a factor of 2. There were astronomers that were arguing it to be 50, and others that said that it was 100. That is the end of this unit on galaxies in the Milky Way. We will talk about, in the next unit, active galaxies and the history of the universe, cosmology.